Have you ever stopped and wondered how a machine actually learns? I mean, not in some sci-fi movie way, but what's really going on inside your phone when it seems to just get smarter? Well, let's pull back the curtain on that, because today we're going to demystify one of the most powerful ideas in technology.
Here's the thing you might not realize. You are using machine learning all day, every day. When you type a search into Google, that's machine learning ranking the results. When Instagram or Snapchat pops a little box around your friend's face, yep, machine learning. And when Netflix just knows what movie you want to watch next, or Siri somehow understands what you're asking for, you guessed it. It's all powered by this one core idea. So how in the world does it work?
You know, way back in the 1950s, a computer pioneer named Arthur Samuel came up with this brilliant definition. He called it the field that gives computers the ability to learn without being explicitly programmed. And that last part is everything. It means instead of us writing millions of lines of code with rigid if this, then that rules, we build systems that can figure out the rules for themselves just by looking at data.
Now, there are a few different ways that machines can learn, but the most common one, by a long shot, is something called supervised learning. And honestly, the best way to think about it is like you're studying for a huge test, but you've been given a complete answer key.
It really just comes down to the data you feed the machine. In supervised learning, all the data has that answer key. We call them labels. The goal is to predict the right answer. On the flip side, you have unsupervised learning, where there's no answer key at all. The machine is just on its own, trying to find interesting patterns. Both are super powerful, but for today, we're going to stick with the big one, learning with that all-important answer key.
Okay, let's make this real. Forget abstract ideas. We're going to build a machine that learns to do something pretty useful. Predict the price of a house based only on one thing, its size.
To do that, we need our answer key, right? So here it is. This is our data. For a bunch of houses that have already sold, we have the input, their size in square feet, and the correct output, what they actually sold for. We're going to feed this whole table to our machine so it can start to see the relationship between size and price.
So first things first, we have to choose a model. A model is really just a fancy word for the machine's starting guess about what the pattern looks like. We're going to start super simple and say the pattern is just a straight line. The machine's entire job now is to figure out the perfect values for W and B in this equation. Basically, the slope and starting point of the line that best fits all those dots on our graph.
And this is the million-dollar question. I mean, you could draw an infinite number of lines through that data. Some would be obviously terrible, some would be kind of close, but one of them is the absolute best. So how does a computer which just sees a bunch of ones and zeros possibly figure out which line that is?
To answer that, we need to bring in an algorithm. And let's think of our algorithm as a tiny hero on a quest. Its one and only mission in life is to find that one perfect line. But to do that, it needs a way to know if it's getting warmer or colder. It needs a way to keep score.
And that scorekeeper is something called a cost function. It's super clever. For any line the machine tries out, the cost function spits out a single number that basically says how wrong that line is. Think of it like a golf score. It measures the total error between its predictions and the real prices. A high cost is bad. A low cost is good.
This makes the whole quest totally mathematical. The best line isn't a matter of opinion anymore. The best line is simply the one that gets the lowest possible score from the cost function. The algorithm's entire goal is to hunt down the line that minimizes that cost.
Now here's an amazing way to picture this. Imagine if you calculated the cost for every single possible line you could draw. For our problem, the graph of that cost would look like a perfect giant soup bowl. The high points along the rim of the bowl, those are the terrible lines with a high cost. And that one single spot right at the very bottom of the bowl, that's our holy grail. That's the one line with the absolute lowest cost. The quest is to get to the bottom of that bowl.
So how does our hero do it? It uses a legendary algorithm called gradient descent. This is the strategy it uses to navigate the bowl. You can think of it as a super simple but incredibly effective strategy for always walking downhill.
And the strategy itself is almost funny in its simplicity. Our little algorithm starts at some random point on the side of the bowl. Then it just repeats a few steps. 1. Look around in every direction. 2. Figure out which way is the steepest path down. 3. Take one tiny step in that direction. And 4. Just do it again, and again, and again, always taking another step in the steepest downhill direction.
By just repeating that simple downhill walk, our algorithm is guaranteed to get closer and closer to the bottom. So let's actually watch this quest unfold, because this right here is the moment the machine actually learns. Okay, so let's watch this happen. On the right, you're going to see our cost bowl, and that red dot is our algorithm on its quest, with every single step it takes downhill. I want you to watch the line over on the left. See how it starts out totally random? But as that red dot gets closer to the bottom, as the cost gets lower and lower, the line just snaps into place. That right there is machine learning in action. It's happening.
And there it is! The algorithm hit the bottom of the bowl. It has found the magic values for W and B that give it the lowest possible error score. The quest is officially complete. Our machine has now learned the relationship between a house's size and its price, all from that initial data we gave it.
So why does all this matter? Who cares about one little line on a graph? Well, because this fundamental process, choosing a model, measuring its error with a cost function, and then using an algorithm to minimize that error, that's not just for predicting house prices. This is the engine at the heart of almost all modern AI. And it's driving a revolution that's estimated to create up to $13 trillion in new value every single year.
So let's just end on this thought. We just saw how a machine can learn to find the best possible straight line through a few data points. But what happens when the model isn't a simple line, but a massive, complex network? And what if the cost isn't about getting a price wrong, but about losing a game of chess or missing a medical diagnosis? That is when this simple downhill quest transforms into the incredible, world-changing AI that we see all around us today.